Hello, scientists. Welcome back. Today, we're going to be talking about one of the most important, but also one of the most controversial sources of electricity in the world. Our focus today is nuclear power. So, to start us off talking about nuclear power, I want to remind you of something that we talked about a couple of days ago. When we talked about different sources of energy and comparing the different ones against each other, one of the main properties that we refer to was called energy density. That can be referred to as both specific energy or energy density. It's basically energy per unit mass or volume of that thing. Basically, how rich in energy is something. Coal is more energy dense than wood, which is why we typically burn coal instead of wood in a power plant. It just takes less of it to produce the same amount of energy. If we put nuclear on the same scale as all of those other fossil fuels we've been talking about, it is essentially off the charts. There is no possible way that you could really compare the energy density of nuclear versus the others. But the way that we harness that energy is very different. So today we're going to talk about specifically how do we harness the energy that has been stored up inside of the nucleus of an atom ready to be released. To get there, we need to talk first and kind of remind ourselves of the difference between fusion and fission. We refer to this in our atomic physics unit. Fusion is when you have two smaller atoms that smash together, become bigger, and release energy in the process. That was happening for anything smaller than really iron 56. In our sun, fusion is happening between hydrogens becoming helium. But those lighter atoms become bigger atoms and release energy in the process. Fission is when a larger atom splits up into two smaller atoms, sometimes produces some other extra neutrons in the process, but also releases energy as well. What we are going to be talking about today is not fusion energy, but fission. Fission is the nuclear power that we are able to use in nuclear power plants today. There's a lot of research going into fusion potentially in the future, but as of right now, a fusion reactor doesn't really exist. All of our nuclear reactors are fission reactors, and our primary fuel is going to be uranium. So as a reminder of what a fission looks like, since that's what we're going to be dealing with today, a fission reaction is when you take something like uranium-235 and add a neutron. That neutron makes it 236, but it's still uranium because the neutron doesn't change the number of protons. That U-236 is incredibly unstable. And it is so unstable that it actually splits up into more than one atom, in this case barium and krypton, and produces some neutrons in the process. Now, those neutrons are really important because they go on to produce this whole thing again. Each reaction can produce 2 or 3 neutrons, and those neutrons can produce new reactions. And this gives us what we call a chain reaction. It's something that if you get it started, it should be able to keep itself going. A great visual of this is using mouse traps in a box and ping pong balls. So check out this quick visual of what a chain reaction might look like if you were able to see it. All right, now let's talk a little bit about the fuel of our nuclear reactor. Uranium, we've talked about before, is radioactive. It undergoes decay because it is unstable. But the property of uranium that we care about right now is some uranium is what we call fissionable. If under the right circumstances, uranium will undergo fission and then produces energy in the process. That's the energy we want to harness. Now, uranium in nature actually is comprised of 2 different isotopes, uranium-238 and uranium-235. Both of these isotopes have 92 protons because that's the definition of uranium. The difference between these two is the number of neutrons they have. And you can see the relative abundance of these two. Uranium-238 is by far the more abundant version of uranium that exists in nature. Only about 0.7% is uranium-235. If you remember back to the slide a couple of slides ago, U-235 is actually the one that we want. That's the one that is fissionable. U-235 can undergo fission, but U-238 cannot. Now, our uranium here in the US comes from a variety of sources. Russia and Canada, some in Australia, are primarily the sources of our uranium. Very little of it comes from here in the United States. Now, that uranium being shipped to us is typically not shipped to us in its raw form. Its raw form looks like this. We call it uranium ore. That uranium is laced within this rock, and shipping that whole rock would be pretty inefficient, that it is not all uranium. Most of it is rock. So that is refined to produce what we call yellowcake uranium. And it's not as delicious as it sounds. Yellowcake uranium is another fancy name for uranium ore. Uranium ore is just uranium oxide U3O8. And this is just this yellow powder that is much more concentrated in its uranium, much easier to transport and to store. Now, that uranium needs to undergo some further processes to get to the point that we can actually use it in a nuclear reactor or a nuclear weapon. That uranium undergoes something that we call uranium enrichment. So that U-235, there isn't really enough of it to be useful yet. 0.7% is a very, very tiny percentage of 235 in that overall uranium. So we enrich it in a couple different ways. One way is called gaseous diffusion. It basically uses the idea that U-235 is smaller than 238. And if you just think about it as less particles, so it's a smaller nucleus and a smaller atom. Now, that 235 can fit through smaller holes. So if you pump uranium gas into a chamber with a membrane here and pressurize it, more of the 235 is likely to get through that membrane than the 238. Now, it's not a perfect thing. There's no easy way to make it so that only the 235 make it through, but there's a higher percentage of 235 than 238 on average that will make it. So every time you go through this process, what you get out the other side is what we call enriched. It's a higher percentage of 235 than you began with. Another common way is using a centrifuge. You may have heard of a centrifuge being used for like blood or blood testing, that if you put blood in a vial and spin it around in this merry-go-round of death really, really fast, the heavier particles go out to the outside because they're heavier, and the lighter particles stay in the middle. Now, in this case, U-238 is our heavier particle. That is going to go to the outside. So if you draw from the inside core, you're going to get a higher percentage of 235 out of that sample. Now, what this looks like for us and what we care about is what percentage of 235 do we end up with? Uranium ore here starts out at 0.7-ish percent. That is what is found typically in nature. Now, there could be some variation there, but that is a pretty solid average. In order to get it to be high enough that we can use it in a nuclear reactor, we need to enrich it to become fuel grade. Fuel grade uranium is about 3.5 to 4% of the uranium is in that 235 variety. And there's a lot of discussion with nuclear power plants and people being nervous that uranium that's used in those power plants could be used to make a nuclear weapon. And something that they aren't really aware of is that uranium isn't exactly the same uranium. Yes, there are parts 235 and 238, but you need a much, much higher percentage of 235 in order to make what we call weapons grade uranium. Now, this weapons grade needs to be about 90% U-235. So I want to give you a visual of what that looks like. Say we take a sample of uranium. This is what it looks like in nature, and obviously it doesn't look like boxes. But as a visual here, imagine that each of these boxes are an atom of uranium. And the green boxes presented here are U-235. The red boxes are U-238. Now, in nature, we have about 0.7% of those are 235. So I've colored about 0.7% of these overall boxes in green. That's what it looks like overall. If I want to enrich that, the way I do it is I'm not actually adding more 235. I can't get extra 235s into the sample. But what I can do is selectively remove 238s. So if I want to enrich that to fuel grade, this sample turns into this. Now, that is a much, much smaller amount of uranium. It takes a lot of uranium ore to produce the uranium that's in fuel grade. This is about 4% uranium. So it's the same number, actually in this visual, the same number of uranium-235 atoms. I've just decreased the number of U-238 until the overall amount of 235 is about 4%. If I wanted to keep going, just to give you a sense of how pure that weapons grade uranium is, going all the way to 90%, my sample turns into this. So this tiny, tiny amount, when we started with that entire screen full of uranium atoms, what we end up with is a very, very small amount. That's why one of the biggest steps in creating the Manhattan Project to produce the first nuclear weapons wasn't building the bomb necessarily itself or detonating it. It was enriching the uranium to a high enough percentage of U-235 and getting enough of that highly enriched uranium to actually build the weapon out of it. Now, what we do with that fuel grade uranium is it is no longer in its yellow cake form. It is then processed to form these uranium fuel rods. And as you see these little pellets, that is the uranium. It stacks into this fuel rod, and those fuel rods are all together known as an array. So an array has dozens, maybe even over 100, it looks like, fuel rods that are in that particular array. That goes into the nuclear reactor itself. And what that looks like inside the power plant is it actually takes place inside this little silo thing here. This is a containment structure. You may be aware of what a uranium or a nuclear power plant looks like. You're probably familiar with this cooling tower shape, kind of that tower with the curved sides like this. There is no radioactive material that actually occurs in that particular part of the facility. All the radioactive stuff is inside this containment structure. Now, those control rods are, or the fuel array is inside this core, and water is pumped past it. The uranium atoms that are undergoing fission produce a lot of heat. It heats up the water, turns that water into steam, and that steam runs a turbine, then goes through a condenser, and the stuff that's coming out of that curved silo thing, that is actually just steam. Cooling down to go back into that process to get heated up and turned back into steam. That turbine, turning electric generator, is what produces the electricity that we ultimately use. Now, that chain reaction is a really, really important factor here. For us to have a nuclear power plant, we actually don't want this chain reaction to go out of control. Those mouse traps that we saw earlier, that was an out of control chain reaction. Basically, it released all of its energy as quickly as it could. That is more of a model of what a nuclear weapon would look like. For a nuclear power plant, we don't want it to go out of control. That's a very, very bad thing. Instead, we want that chain reaction to be just enough that it keeps itself going but doesn't get bigger and doesn't get smaller, that it pretty much stays the way it is. Now, there are some important factors here. Only about 4% of the fuel is actually fissionable. That uranium-235, only about 4% of it can actually undergo this process. And the neutrons to produce that fission reaction have to be moving at a relatively slow pace in order to be captured by that uranium-235. So the way that this is produced is there are two main features of the nuclear power plant that we have to play with. The first is the moderator. A moderator is typically used as water or graphite. This is what our fuel rods are submerged in. So here, we can see them down here. The purpose of this moderator is to slow down those neutrons. Water actually does a very good job of insulating against fast-moving particles. And as neutrons travel through water, they slow down. So the primary purpose of the water inside that fuel array is actually to get them slow enough that they can then produce a further reaction. We also have some control rods that are inside that array. The control rods here are represented in these green bars. Control rods are typically made out of something boron. The purpose of boron is it is a very good absorber of neutrons. So if a neutron hits a control rod, it gets absorbed and then cannot go on to produce another reaction. Now that leaves us with three possibilities. We can have a neutron that comes out of here and flies away and actually goes too fast. If it is not slowed down, too fast, it blasts right through that U-235 and doesn't produce anything. We could have a control rod where that neutron instead hits the control rod, gets absorbed, and then doesn't produce a reaction either. The third option is we have it traveling through our moderator, the water. It slows it down, and if it slows down just enough, it can get absorbed by the 235 to produce another fission reaction, produce some more neutrons, and then go on to produce another chain reaction.